Alright, so this is the recording for simple harmonic oscillations. Make a copy of your student presentation, fill in the missing information and make your notes, turn it in on Canvas. I'm using the teacher presentation for you. And I already have a copy here. I'm gonna go over the slides and solve the examples for you. Just follow me. This is for my physics students at Northside High School. I am Mr. Baute. Today we're doing simple harmonic oscillations, simple harmonic oscillators, spring mass system, simple pendulum, energy in a simple harmonic oscillator, damp oscillations, force oscillations, and resonance. How do the acting forces affect the motion of the student? The net force is pulling the student back inside the boat. Simple harmonic oscillations, or SHO. Objects, after being put away from its rest position, move back to the equilibrium position, making simple harmonic oscillations. Simple harmonic oscillations are the simplest periodic motions you can have, so you can represent them using a simple sine or cosine function. There are two conditions for simple harmonic oscillators or oscillations to be present. You have to have a restoring force that takes the object back to equilibrium. That restoring force should be proportional to the position of the object. And you have to have also an inertial factor represented by the mass. When the object passes by the equilibrium position or reaches the equilibrium position, it keeps moving to the other side, and then the process becomes cyclical. So you can measure the number of cycles, you can measure the distance the object is moving away from the equilibrium position. The maximum distance is called the amplitude. You can measure the period, which is the time for one cycle. And you can measure the frequency, which is the number of cycles it makes in a second. These are check questions. I'm not going to go over the answers for this one. This one is for you to answer. Typical oscillators, spring mass system, simple pendulum. You can see the period is proportional to the mass and inversely proportional to the spring constant on a spring mass system. That means that if you increase the mass, you also increase the period, but if you increase the spring constant, then the period decreases. In a simple pendulum, the period is proportional to the length of the pendulum and the gravitational pull of the planet. So that means that if you double or increase the length of the pendulum, that will increase the period of the pendulum. It will take more time, right? And if you increase the gravitational pull, then that decreases the period. It's going to take less time. Frequency and period by definition are the opposite of one another. Frequency is the inverse of the period. Period is also the inverse of the frequency. The equations for motion, the position is equal to the amplitude of the motion times the cosine of the angular frequency times time. What is angular frequency? Well, it's 2 pi divided by the period, or 2 pi f. In other words, it's the same as frequency, but in other units. Remember, pi is 3.14. This is a typical equation for position time graph, where you can see one complete cycle, and so you can represent the cycle in a position time graph. So you can measure the period and the amplitude from this graph. You can also get the same information, although it's a little bit more complicated, for the velocity time graph. It's right here. and for the acceleration time graph right there. Practice 1. A pendulum makes 200 cycles every 20 seconds. What is the frequency? All you need to do here is apply the concept for frequency. Frequency is cycles per second. So it's going to be 200 cycles divided by 20 seconds. That is 10 hertz. Okay, or you can write it down Hz, 10 hertz. That's the frequency. Practice 2. A pendulum makes 160 cycles every 8 seconds. Determine the period of the pendulum. All you need to do is apply the concept. Period is seconds per cycle. How many seconds it takes to make a cycle. So the period will be 8 seconds divided by 160 cycles. How much is the period? Pull out the calculator. 8 divided by 160, 0.05. 0.05 seconds in a cycle. That is the answer. Simple pendulums follow the law of conservation of energy. Energy is sometimes potential, like in point 1, sometimes kinetic, like in point 2, sometimes potential, point 3, and then the pattern repeats, but when you add potential plus kinetic, you always get the same total. So you can say that the total energy of the pendulum is equal to its kinetic energy plus its potential energy. So we can use this as an example. Here you have a simple pendulum of 2 kilograms of mass. It has a potential energy of 256 joules. At the highest point, what is the velocity at the equilibrium point, or the lowest point? Let's do that. Okay, givens. The mass is 2 kilograms. The potential energy 256 joules. What do we need to find? We need to find the velocity at equilibrium. How? Well, let's put it the other way. Potential energy equals kinetic energy. Potential energy at point 1 equals kinetic energy at point 2, if you want to put it that way. Oops. Okay. Which means that 256 joules will be equal to half the mass times the square of the velocity. So you can find the square of the velocity as 2 times the mass, which is 2 kilograms. I'm sorry, let me put it this way. Times 256 joules divided by the mass, which is 2 kilograms. All right, and that will give you 256, whatever units, meters squared per second squared. So if you have the velocity square, the square root of the 256 will be equal to the velocity. So we can pull out the calculator. The square root of 256 is 16, and that will be meters per second. That's how you do it. Okay, took some time. Yeah. In a spring mass system, things are similar, except that we're going to consider a spring mass system that is oscillating sideways. In this case, in position 1, the energy is in the form of potential elastic energy. In point 2 is as kinetic energy, and in point 3 is as potential elastic energy. As you can see, the energy flow from kinetic to potential to kinetic, but the total remains the same. So you can write down that the total energy of the system equals half the mass times velocity squared plus half the spring constant times the stretching length squared. And you have this example: a spring mass system has a mass of 2 kilograms and a spring constant of 4 newtons per meter. When the mass is stretched 0.4 meters, it is released and it starts to oscillate, start doing oscillations. What is the velocity at the time it passes by the equilibrium position? Same situation or similar situation. So we have the mass. So how much is the mass? The mass is, it says 2 kilograms. All right, same mass as before. K is 4 newtons per meter, and X is 0.4 meters. Is that correct? Let me check. Yes, yep. So we need to find the velocity, right, at the equilibrium point. At equilibrium, okay. So we can say that the elastic energy on the spring will turn into kinetic energy at equilibrium point. And so that is the equation. So we can write down the equations. We don't have the elastic energy, so we're gonna have to write down the equations. So we have 1/2 k x squared equals 1/2 mv squared. 1/2 is cancel out. You get that v squared down here. Give me a second. It's giving me a hard time over here. Alright. So v squared is equal to kx squared over m. So plugging in the numbers, we get 4 times the square of 0.4 divided by 2. So let's do that. So let's do the square first, then multiply by 4 and divide by 2. You get 0.32 meters squared per second squares. All right. V, the velocity will be equal to the square root of 0.32. How much is that? Well, let's do it here. The square root of that number is 0.565, 0.57 rounded. All right, that's going to be 0.57 meters per second. And that is the solution to that problem. All right. Friction slows down the system because some of the energy of the motion is passed to the molecules and the surroundings, causing the mechanical energy of the system to decrease. Oscillations for which friction cannot be ignored are called damp oscillations. They're not simple anymore. This is an example of a damp oscillation, a spring mass system that is submerged in a liquid, like oil. You're going to have three different outcomes depending on the conditions. You can have a critically damp oscillation where the system reaches equilibrium the fastest way, like car struts. Overdamp oscillations take a longer time to reach equilibrium position, like door jacks. And underdamp oscillations make several oscillations before stopping, like a playground swing. Question number 5 is a check question. This is for you. Oscillations in which friction cannot be neglected are called? You tell me. Force oscillations. Well, you have an example of a force oscillation right there. Force oscillations are present in a system when you have an external force pushing at certain specific times. The system is being forced to oscillate at a frequency set by an external periodic force. When the natural frequency of the system is approximately equal to the frequency of the periodic force, then resonance is observed. Resonance happens when the amplitude of the oscillations dramatically increases when you have a periodic force acting on the system. It is defined as the sudden increase of the amplitude, A, of the oscillations when the frequency of the system matches the frequency of the external force. Question number 6. The sudden increase in amplitude for a force system is called? You tell me. This is your exit ticket practice assignment. Given the x equals 20 times the cosine of 12 times t, draw the position time graph, draw the velocity time graph, and draw the acceleration time graph. All right, we can do the position time graph. We're going to use the equations. So for position x equals a cosine of omega t. And the formula is telling me that the amplitude is 20 meters and the angular velocity omega is 12 radians per second. Okay, so we can apply, let's see, it's here, it's going to be, let me try this one. So we start from here. Okay, and then from here, and here we can do the second half of this. There you go. And now we can have this line. This is going to be the period. Okay, so the amplitude is already there. How much is the period? How much is the period? to calculate it. So omega is 2 pi divided by the period. So that's the estimate that the period is also 2 pi divided by omega, and omega is 12. So that means that this is 6.28 divided by 12. Put this number here. So that's the math you need to do to find the period. So how much is the period? Let's pull out the calculator. 6.28 divided by 12, 0.523. So this is 0.52 seconds. Let's round it to that. So that's how you get the period from the angular frequency. Okay.